I wish you all the best, and I'm very happy. So, and now I introduce the first talk of this afternoon, the first talk in person, and we receive Professor Damien Gaboriau. He's a CNRS from École Normale Supérieure de Lyon, and today he's talking about on the homology torsion groove for some classical groups such as SCLZ, Artin groups, and mapping class groups. So thank you so much, Professor. You can start whenever you want.
Thank you very much. It's a great pleasure to be back here in Brazil after 25 years. I will come back on that later on. Okay, so first of all, let me give you a crash course about homology and torsion in the homology. So if you have a manifold with cellulated manifolds, or more generally a CW complex, you can associate the homology of this space X as soon as you have chosen a ring A. So first of all, you start by considering the space of chains, which are formal linear combinations of G cells. Okay, so it's sum of A sigma times sigma for sigma a cell and A sigma an element of the ring. And of course, you know that you have the boundary maps sending one space of chains to another one of dimension 1 less. And if you compose twice this boundary map, you get 0. So that this means that the image is contained in the kernel of the next one. And the homology precisely measures the default of this injection to be an equality. And so one defines the homology as the quotient of the kernel of one map modulo the image of the preceding one. Okay? So if, for instance, A, the ring is Z, then recall our space X is compact, so that you have finitely many cells. So in particular, all of this space of chains are finitely generated free modules. And thus, the homology becomes an abelian group, and moreover, a finitely generated abelian group. And such a group decomposes as a torsion-free part, plus, of course, the torsion part. And the torsion-free part has the form Z to the BG, and this BG is what we call the Betti number, the Gth Betti number of the space. Okay, so this is Z to the power, excuse me. Oops, and you have this torsion part, which is of interest for me. This is very difficult in general to compute, to estimate. If A, instead of being just a ring, is in fact a field, then your quotient space, the homology space, gets the structure of a vector space. As such, it has a dimension. And this dimension is now the Gth Betti number of X with coefficients in the field K. Okay? Just an observation, if A is a finite field, let's say FQ, then just notice that this vector space is a finite set, stupidly as a set. So its number of elements is just the cardinality of the field to the power, the dimension. And thus, you get this dimension just by taking the logarithm. And this is to motivate the fact that a logarithm will appear in a small moment. Okay? Now observe that if X tilde, the universal cover of X, is contractible, then it is not difficult to check that what you get as this homology invariance is indeed independent of the choice of the space X you took. If you take another one which is also with contractible universal cover, you get the same quantities. Okay? And thus, you define this homology groups as invariance of the group. So, homology of the group. Okay? If X tilde universal cover is only deconnected, meaning that, of course, it is simply connected, and if you assume it is two connected, which means that every, well, you know what two connected and deconnected means. So if it is deconnected, then the invariance you get for the group are just up to degree d. Okay? So if you take another space Y with a deconnected universal cover, then you get the same invariant up to degree G equals D. Okay? And so here are the objects I'm interested in. The homology of the group with coefficients Z, the torsion part, and also the analog when the ring is a field. Okay? So these are invariants for the group or for the space also when it is when the universal cover is contractible. Okay? Well, indeed, these invariants are in general quite hard to compute. Okay? So after this small crash course, I would like to emphasize that this is a modern presentation, of course, of homology. Modern means after Emmy Noether. Indeed, this was, these Betti numbers come from Riemann. Riemann who defined these numbers for surfaces, the number of curves you can draw on the surface without disconnecting it. This gives you an invariant of the surface. Okay? And indeed, Riemann was of fragile health, and he used to spend time in Pisa, where the weather was much better than in Göttingen. And there, he used to discuss with Betti. And together, they tried to extend to higher dimension these invariants discovered by Riemann. Okay? Well, indeed, they did not publish anything together, and Riemann died in 1867, I guess, or 66. And one has some insight about their discussions thanks to the notes we found in the stuff of Riemann after his death. And so there is nothing really constructed there, but just some ideas. And some years later, Betti published a paper. And essentially, well, he was really succeeded in defining some invariants in some degrees, and it was not that clear. I tried to read that paper in Italian, and the Italian is not the problem. It's very difficult. And then a Poincaré in a short note about a problem of Euler, generalization of a problem of Euler concerning polyhedron, something like that, where he introduces indeed the Euler characteristics for polyhedron. There he mentions these numbers discovered by Betti and Riemann, or Riemann and Betti, and then some lines later he just names them Betti numbers. This is where it comes from. This, but at that time also, you know, there was this irritating young student, Egard, who wrote to Poincaré to mention that there was gaps in his paper, his famous analysis situs paper from 1995. Okay, and indeed, one problem was serious, and another one was a counterexample, according to Egard, of the Poincaré duality. And his counterexample was just the RP3, the projective space of dimension 3, which is orientable. But indeed, according to a computation Egard did, he found that the Euler, the Poincaré duality was not true. But the problem indeed in modern language was just that Poincaré considered Q coefficients, rational coefficients, while Hegard and Betti, in a sense, considered, well, coefficients indeed in Z over 2Z, or F2, the field with two elements. Okay? And the problem came then from that. And then, so Poincaré worked, continued to work on that, and he was a bit irritated with this problem of that the numbers were not exactly the same. And then he realized that come in, well, in modern terms, this is the torsion. But for him, it was just a combinatorial topology. So he had complexes glued together along faces, and then considering the incidence matrices and the theory of reduction, if you want, then you can diagonalize the matrix in a sense and get integer on the diagonal such that each number divides the preceding and so on. You know this theory. And these numbers were defined by Poincaré as the torsion number, torsion Betti number. It was not rank or the cardinal of any group. It was just number. And he named them torsion Betti numbers because he thought that the problem came from the fact that the manifold was twisted. And the name, we still use the name torsion to name finite order elements in groups. This is strange. Anyway, it is only when Hopf and, oh my God, I forgot the name. Yes, Alexandrov, of course. So Hopf and Alexandrov came to Göttingen in the 1925, 26, 27, and they gave series of lectures about combinatorial topology. And then when they explained the theory of Betti numbers and so on, Emmy Noether, attending the talks, noticed immediately, why don't you use the modules here and take the quotient? This is so simple. Your numbers, and she did not write anything about that, but both of them, Alexandrov and Hopf, in their memories explain how she explained to them the deep locus where the homology lives. Okay, so these invariants are interest for geometers and also for group theorists. Okay? So I said there are to compute. And as usually mathematicians do, we change the problem. Instead of computing them exactly, let's consider asymptotics. Okay? So, for instance, we consider certain sequences of finite index subgroups. I will come back on that, which means that you consider finite covers of your initial space. Okay? And if you think in the Schreier formula, you immediately see that the right way to normalize is by the index, or the Euler characteristic being multiplicative in the index. This is the right normalization. Okay? And so you consider if you have a field, the dimension of the homology in degree G for the field K, divided by the index. Or for the torsion, you take the log of the size of the torsion part. That log was not a joke, you see? So you take this logarithm of the size of the torsion divided by the index, and you ask for the asymptotic behavior. And just another related invariant, which is the rank gradient. It has been introduced by Lackenby. And this is just the rank as defined as the minimum number of generators for this finite index subgroup. You have your gamma and the finite index subgroup gamma n. They are finitely generated in our context, okay? And so, and it's very difficult to compute the minimum number of generators of a group like that. Anyway, this the rank of gamma n divided by the index, and its limit is what we call the rank gradient. Observe that already, Poincaré already knew that H1 was the abelianization of the fundamental group. Okay? In particular, B1, the first Betti number, is bounded above by the rank. Okay? Good. So now I present the type of theorems we found with Habert, Bergeron, and Franchik. So this is essentially joint work, what I will explain. And the type of result we obtain is the following. So you consider a group, gamma, which is finitely generated, residually finite. Then you take a certain sequence of finite index subgroups, such that so the condition on the sequence will be discussed in just a second. Condition A. Then, for every degree in the range, 0, 1, up to alpha, alpha depending on the group, we claim that the growth of the homology with coefficient in a field K, in any field K, tends to 0. Okay? And concerning the torsion, the same result, it tends to 0. Okay, so now I have to tell you which kind of sequences we consider and which kind of groups and the corresponding alpha. Okay, this is clear? Good. So the type of sequences we consider are, in general, Farber sequences. Before giving you the definition of a Farber sequence, an example of Farber sequences is given by residual towers. So it's a sequence of a decreasing sequence of finite index subgroups. Each of them is normal in gamma, and the intersection is trivial. Okay? So this is an example of Farber sequences. Of course, when you take finite covers of that space, according to such a chain, you get larger and larger finite covers that approximate the universal cover in a sense. Okay? Yeah? Yes. If it is residually finite, you always have a residual tower. Just because of, well, if you have a finite index subgroup, it contains a normal finite subgroup, a finite index subgroup, normally in the big group. So you can always construct residual towers. So more generally, a Farber sequence is a sequence of, well, there is this algebraic definition. You count for every non-trivial element of the group the number of conjugates of gamma n that do contain gamma divided by the total number of conjugates. And you want this to tend to 0 for every non-trivial element. Okay? In geometric terms, this means that the injectivity radius tends to infinity from most of the base points. Okay? When you choose a base point or you choose a point in the one skeleton or the 0 skeleton, and you take the covers, and of course, you have many more vertices in the successive covers, and you want that from the point of view of most of the points of the vertices, the injectivity radius is large. Okay, so more precisely, for every R, size of the ball or injectivity radius, you want that the number of vertices in the 0 skeleton of x tilde mod gamma n, so the number of vertices where the injectivity radius is larger than R, divided by the total number of vertices, tends to 1. This is clear? So from your manifold, if you think in a manifold, has large injectivity radius, except maybe in a few places. Okay. Now, so that's clear? And if it is not clear, just stick to that example. Now, the type of groups we consider, so it was in my title, so we consider such groups as SLDZ, then alpha equals D minus 2. Okay? So I remind you, alpha is the top of the range of the degrees where you have this sequence tending to 0. Okay? If you take the mapping class group of a surface of genus G, then alpha equals to G minus 2. With Yacine Gersh and Camille Orbet, we found that for the group OUT of Wn, which is the group of outer automorphisms of the free product of n copies of Z over 2Z, for this group, alpha equals n over 2 minus 1. Okay? And if gamma is a residually finite Artin group, then we want it to satisfy the K pi 1 conjecture, which is, well, conjecturally it's satisfied for all the Artin groups. It is known for few of them, but okay. And you may know that an Artin group is built out of a nerve, and you want, so it's a compact space, and you want this compact space to be deconnected. Then alpha equals D minus 1, D plus 1, sorry. If you are less interested in Artin group, don't worry. So I hope that among these groups, one of them could attract your interest. Okay. Previously on Globo, we had the situation when the field was the rational, and then the Luc, the celebrated Luc approximation. Luc proved something that was conjectured essentially by Gromov, that the limit is, first of all, that it converges, and that the limit is a well-identified quantity, the Gth L2 of the group. So when you have groups, Chigger and Gromov find a series of invariants. They're L2 Betti numbers. They are defined for every degree, unlike for the usual Betti numbers and groups that lack some finiteness properties. Okay? Anyway, the Luc approximation theorem claims that the quantity we are after, this growth, converges and to the corresponding Betti number. Okay? And so as a corollary, and this was in a sense the interest we had when we worked together with Yacine Gersh and Camille Orbet, we get the annulation of the L2 Betti numbers of that group, OUT Wn, up to degree alpha corresponding to the group. Okay? Is it clear? So, in general, the behavior of these sequences is quite complicated and tricky to understand. It is not even obvious that it converges. It may converge, well, is it independent of the sequence, which is a kind of the same question. And in general, what can we say about the limit? Okay? Do we have a candidate? When the field is Q, yes, we have a candidate. For a finite field, it's really a big mystery for a moment. Okay. Previously continued. In the case you consider a sequence which is strictly decreasing, of finite index subgroups, no assumption about normality nor about the intersection, you can associate the profinite action on the boundary of the projective tree associated to that, auprès de mon arbre. Okay, so the tree, you know, the first level is just gamma over gamma 0, gamma over gamma 1, gamma over gamma 2, and you have this tree of, how is it called, of cosets, this tree of cosets, okay? And it has a boundary, of course, and the group acts on each level so that it acts on the boundary. On each level, you have a unique invariant measure, which is just atomic measure on the finitely many points, you see, the fair measure. And so, in the end, you have a topological counter action with a unique invariant measure. Okay? And this is this type of action Olga alluded to this morning. If gamma is the fundamental group, let's say, of some complex or of a manifold, then you can consider the diagonal action of gamma on the universal cover and of this finite, of this counter set, counter space. Okay? And so you consider the diagonal action on the Cantor times the universal cover. And then you consider the quotient space. This quotient space is a foliated or laminated space with a transversal measure. Okay? This was my duty to say foliated space. Okay? So, with Nicolas Bergeron, some years ago, we proved that, so in this context, where it is not exactly Luc approximation theorem, you see? So we have the same field, just the sequence is not made of normal subgroups. Okay? So what we proved is that indeed the quantity considered by Luc, so m tilde mod gamma n, the Betti number with Q coefficient divided by the index, this tends to a well-identified number, which is the Betti number of the foliation in the sense of cone. Okay, so this is a generalization of Luc approximation theorem. And so in particular, you can do that for Farber sequences. And you have a Farber sequence exactly when the action on the boundary is essentially free from the point of view of the measure. This is the meaning of Farber sequence. And indeed, in the meantime, Farber had extended Luc approximation theorem to these sequences. And now we call this kind of sequences Farber after him. Condition for a sequence, well, to produce some, well, it was not his point of view. The point of view was the algebraic one, the number of conjugates that do contain blah, blah, blah. Okay? And now if you consider a decreasing sequence of Farber, then now it's Farber sequence, okay? So the limit is free. It is free in the sense of the topology, and it is also free in the sense of the measure. This should connect with some, with the talk of Olga this morning. Okay? Abert and Nikolov, so I remind you that B1 is smaller than the rank. And so Abert and Nikolov proved that these tend to the cost -1. I don't want to enter exactly in this theory, the theory of the cost. So it's an invariant for dynamical systems which preserve a measure. It has been introduced by Gilbert Levitt some years ago. And this is essentially on that I worked when I spent 1 year here 25 years ago. And so I wanted to thank again the UFI, the IMPA, FAPERJ also, and especially so UFI and IMPA, who gave me an office so that I had this opportunity to work at Copacabana. Pretending I was in the other place. Okay, so from that, we have many examples of groups for which the cost is always 1. For instance, SLDZ and, well, many groups satisfy this property, which means that here we have 0, and this gives something about the first Betti number and the behavior of the sequences. Okay. Just yes. Yes. No, just of gamma n. The minimum number of generators of gamma n. Indeed, my greatest achievement when I was here was my participation to the Carnaval when the Viradoro of Niteroi won the Carnaval. So I was part of it. I'm very proud of that. Okay, now I'm a bit short in time. So there are some results of that kind in the amenable context. Also, Brighton and Koshlukova introduced a notion of slowness, and they obtained some results of the kind we have for the growth of the Betti numbers with finite fields, for limit groups, for certain graphs of groups. They control the number of cells. Okay, and also, but I have no time to enter that. There are very nice results of Avramili, Okun, and Shreve for right-angled Artin groups. So I advise you to have a look at that if you like right-angled Artin groups. And also for manifolds, we have bounds in terms of volume, following works of Sauer, Bader, Gelander, and Sauer. For instance, if your manifold has a sectional curvature contained in a closed subinterval of -1, 0, 0 excluded, then there is a constant which depends only on the dimension, so that for every manifold, okay, the logarithm of the size of the torsion of the part, of the torsion part, is bounded by the volume times that constant. Okay, so this gives some estimates for the growth of the torsion. Okay, so let's come back to our result. I would like to let you observe that my co-authors are Miklos Abert, Nicolas Bergeron, and Mikolai Franchik. 3 Nicolas in different languages, like, you know, the 3 Musketeers. Who is D'Artagnan? Okay, so some words about our tools. Our main tool is what we call the chip rebuilding property. And we introduce this alpha, which means that up to dimension alpha. Okay? So the chip rebuilding property, I will give you an example of what it is with tori. Okay? If you have a torus, gamma equals z to the d, then the space X is just Rd mod z to the d. So it has a certain number of G cells. Now if you take a finite index subgroup, the cover is again a torus. It has much more cells, indeed exactly the index times the number of initial cells. Okay, so it's something like that. Quite a complicated cellulated space. Okay? And rebuilding consists essentially in that. reconstructing the space using less cells. Okay? And then we will exploit the presence of nicely embedded tori-like subcomplexes in the space X we had in order to, well, use that observation. Just a point. If we want to get a grip on the torsion part, we need to use a proposition due to Gabor, which says that the logarithm of the size of the torsion is bounded by the number of cells times, well, essentially the norm of a boundary map, of one of the boundary map. So that to have some information on the torsion, we must, in the reconstruction, have a control on the norms, okay? Which means that we cannot just repeat complicated cellulation by one cell in the case, in dimension 2, let's say here. Because then one of the transfer map, H or G, will have non-controlled norm, okay, along the sequence. We want a kind of a uniform bound. Okay, now I will give you a floppy definition of the chip rebuilding property. So all the groups are residually finite, and we say that gamma has a cheap alpha rebuilding property if, first of all, gamma admits a finite B gamma, at least up to dimension alpha. And second, for every positive epsilon and every Farber sequence, for a large enough n, we can rebuild the intermediate cover x tilde mod gamma n using, well, few cells and using a yn which has a finite alpha skeleton, which has a proportion about epsilon of cells compared with that of xn. Okay, so you have these covers and you rebuild step by step, stage by stage, okay? And so you want about epsilon times the number of cells and a control on the norm. Something like a polynomial in 1 over epsilon. Okay, now I will present you very quickly the real definition of chip rebuilding property. Okay, you prefer the floppy one, but it is the same. Really, it's the same. And you have here all the maps we want to, the norm to be controlled, okay? In this homotopy equivalence between the chain complexes. This makes sense? Okay, and of course, you don't want to check the property for a given group, especially for SL3 or SLDZ. You don't want to check it. But we, and you don't have to, because indeed, well, we have a technique that allows us to bootstrap and to check the property successively for larger and larger classical groups. And so why is it good, this property, alpha chip rebuilding property? It is exactly because this gives what we want for the limits of the growth. Okay? So now it remains to establish the alpha chip rebuilding property for the groups in B, SLDZ, mapping class group, UT WN, and so on. And for that, so we use the following properties. So first of all, Z to the N has the chip rebuilding property for every alpha. Easy to check. And now we have this bootstrap theorem. Assume gamma acts on a CW complex omega. Gamma is always residually finite, so it acts on a complex, and in such a way that the quotient at finite alpha skeleton, upstairs the space is alpha minus 1 connected, and something about the cells and the stabilizer of the cells. Okay? You want, for a cell of dimension G alpha, you want its stabilizer to have the alpha minus G chip rebuilding property. Okay? The larger the dimension, the weaker the property. And in this situation, if you have that, then gamma, I will show its real as the chip alpha rebuilding property. Okay? Just let me mention that a finite group, in particular the identity, the trivial group, do not have the chip rebuilding property. So we really need, for this theorem to be applied, we really need three and quite large stabilizers. At least, well, for instance, if you have infinite abelian groups as stabilizers, Z to the D, this is good. Okay, you can get more information about the gamma itself. And so, as a corollary, we get that the chip rebuilding property is an invariant of commensurability. If you have a normal subgroup, which is infinite, so with the chip rebuilding property, so that the quotient is of type F alpha, so it admits B gamma with finite skeleton up to dimension alpha. Then the group itself, in the middle group, gamma, the quotient, and the kernel. The kernel is supposed to have the chip rebuilding property and the quotient to have good finiteness properties. Then gamma itself has the chip rebuilding property. And now, for our examples, for our groups, for SLDZ, the omega you will take is just the rational Tits building. Okay? When you have SLDZ, you have this building which is made after considering the action of SLDZ on Q to the D. Okay? And the flags of subspaces of strictly increasing dimension, these flags of subspaces give you the cells of the Tits building. Okay? And in this case, the cell stabilizers are exactly the parabolic subgroups, P. A parabolic subgroup contains a unipotent subgroup, as a normal subgroup, which itself contains a Z as a normal subgroup. So what you see, bootstrap from Z to the unipotent parabolic, and these are the stabilizers. And now the only constraint is about the homotopy type of omega. Because I remind you here, you have this condition. The condition on alpha is really now here, the constraint. What is the connectivity of the space omega? And by Solomon Tits, we know that the rational Tits building has the homotopy type of a bouquet of spheres of dimension D minus 2. So it is D minus 3 connected, and this gives alpha equals D minus 2. Okay? For the mapping class group, have a guess, of course, the curve complex. Okay, so you know it's the number of curves, the curves that you draw that do not intersect, and so, and this also flags in the sense of such curves. The cell stabilizers contain a normal subgroup, which is a Z2DM, virtually. So the stabilizers have the chip rebuilding property for every alpha, and so has the mapping class group, as soon as we know the homotopy type curve complex. Okay? And the work we did with Yacine Gersh and Camille Orbet was exactly to build and to find the correct omega for the group UT WN. Okay? And for the Artin groups, so you have to consider the case when they are spherical and the other ones. But I guess it's time to stop.
So thank you so much, Professor Gaboriau. So let's see if the audience, if we have some questions or comments. Any questions, comments?
So I'm just trying to see if I'm just trying to see if I got this, if I'm understanding this correctly. So you have a group and it acts on a cell complex. You take a finite index subgroup and that acts on the same cell complex. And what you want to do is you want to change the cell complex. Yes. And the point is, if you didn't change the cell complex, then you have a canonical embedding, which is just the identity, so it's unit norm. But when you change the cell complex, then there's going to be an embedding of this guy into the first guy, which could have very large norm, and you want to have a control on that, and that's what you're trying to do. Is that right?
Yes. So you change the cellulation. You take a space which is homotopy equivalent to X tilde mod gamma n.
Right.
Which has, well, so if it is homotopy equivalent, then at the level of homology or chains, you have this homotopy equivalence of complexes.
Right.
Okay. And so up to degree alpha, you have finitely many cells.
Right.
Okay. And so what you want is that the number of cells in Yn is of type kappa times epsilon, the number of cells in Xn.
Right, I see. So you want this guy to be small-ish.
Yes. And so you don't rebuild then Yn, but it's always Xn that you rebuild.
Right, okay. And the point is that the maps that you make in order to can't be too big either. That's the point. So you need this balance.
Yes.
Yeah. Right.
I just have a related question. You said that you want a polynomial control. On the
yes.
Does the degree of the polynomial have some meaning, or what is it?
So here, not exactly, but in some situations, you can say effectively more things, especially when you consider how is it this subgroup that are the kernel of the map to SLD Z over PZ, the congruence subgroups. In the case you consider congruence subgroup, we can say more, and so we have to control a little bit more seriously the norm, and so because it tends to 0 for this kind of Farber sequences, it tends to 0, but we have also information about the speed of the decrease to 0. And for that, we need some information about the degree. Yeah.
So any other questions, comments? So let me see if in the YouTube you have some questions. Okay. So let's thank the speaker again.
And at the point.
So we have something like 1 or 2 minutes before the next talk. It's okay?